has these kind of galaxies, as we can see here on the upper left corner of the figure. And then classical dwarfs go all the way down to stellar mass of 10 to the 5. And then the ultra-faint dwarfs that really sort of entered our life only in the last maybe 20 years, when they were detected in the halo of the Milky Way, go all the way to 100 solar masses. So why do we even need these definitions? One thing is that astronomers like subgrouping of stuff, right, in galaxies, but also because these galaxies, they span a huge range in stellar mass, and the physics that sort of govern their evolution is very, very different. In fact, one of the really fun discoveries from the last year is this Unions 1 galaxy, which has a stellar mass of 16 solar masses. Its absolute magnitude is positive, okay, as a plus. People always get confused. Now, I don't work on these ultra-faint dwarfs, and I'm not going to talk about them because we're not quite there in finding them beyond the Milky Way, but I think you would agree that this Unions 1 galaxy is very different from the LMC, right? Like, why should we talk about them the same way? So, names. Okay, quick one slide of background. There is a lot of science that can be done with dwarf galaxies. These are what we think the first galaxies to form in the universe. And we think they might have reionized the universe early on. There are also the building blocks of more massive galaxies by merging with each other and by the accretion into the halos of more massive galaxies. If we want to understand the Milky Way, perfect timing, David. If you want to understand the Milky Way, then, or generally the assembly of massive galaxies, then dwarf galaxies are part of the Milky Way ecosystem. Especially if you want to do cosmology with one galaxy, let's understand the dwarf galaxies. They are extreme in many ways. They are the oldest, the most metal poor, the smallest and the least luminous galaxies. And finally, one of the big picture selling points is that they are important for testing predictions of lambda CDM or cosmology on small scales, in part because they are small scale, right? They live in the small dark matter subhalos. And we think they are dark matter dominated. So perhaps they provide this more pristine view of the skeletons of dark matter halos, or maybe not. Why do we want to study dwarf galaxies beyond the local group? Indeed, in the local group, this has been a very fruitful line of inquiry. And there are many successes for understanding or testing lambda CDM with satellites of the Milky Way, but also some tensions regarding how many of these satellites we have and their distribution inside the halo. And some of the solutions were sort of either let's change the dark matter model, or let's change the baryonic model, galaxy formation model, or some combination of the two. Now this is great, but the Milky Way only has about 100 dwarf galaxies. They're all affected by the Milky Way. Maybe there are other types out there. We just want more statistics, so we need to study dwarfs beyond. So this is the regime that I'm going to talk about, okay? Everything that is beyond the Milky Way. Not going to go too far in redshift. But this is important for putting the Milky Way in context, right? This is super crucial if we want to interpret the Milky Way. Everything's okay?
Yeah, can we just click the exit up there?
The what?
On the meeting.
There.
And probably X on beautiful. Thanks.
Okay, perfect. So, for any interpretation of the local group and the Milky Way M31, we want to have sort of a bigger context. Also for increasing the statistics, finding new types of low mass, low surface brightness galaxies that do not exist in the local group. Understanding what the environment is doing, this is a crucial point, this is hard. And also potentially enable some new tests of lambda CDM by finding all of these other things. And I'll give examples for some of them. Okay, so some of the reasons that dwarf galaxies are so interesting, the fact that they don't have a lot of stars and they are small, is also what makes them so difficult to study. So here is the Sculptor dwarf galaxy, so it's a Milky Way satellite. And this one, similar to other Milky Way satellites, was detected by finding the individual stars, sort of overdensity of the bright red giant stars in this galaxy. But when we look at this galaxy further away, we see these smudges, right? So we need to think about, this is a very basic Astro 101 figure, so sorry, but I'll go over it really quickly. We need to think about these things in terms of surface brightness rather than brightness, which is the brightness divided by unit area. So all of these 4 circles or galaxies have the same total brightness, but the one on the right there has much, much lower surface brightness, right? So this is what we need to talk about. And so until the mid-90s or so, this was done mostly with photographic plates, this example that we can see here. This wasn't bad. Some of these surveys even covered a pretty wide area, but we needed to find, I mean, not me, I wasn't doing astronomy at the time, but people needed to find these galaxies just by eye, right? So it was sort of hard to do something systematic, understand the selection bias of your survey. So it was quite limited also in terms of depth. So this 24.2, it's not bad, but we still have sort of at least 6 kind of orders of magnitude to push. And then late 90s, early 2000, there was a big shift, right? When we started having, again, not me yet, surveys with CCDs like SDSS. And that provided improvements in many aspects. One, we covered much, much larger areas of the sky. There were some new techniques that allowed improved flat fielding, which helps us with actually finding these galaxies. But I would say mostly, I think the automated detection and the fact that we can quantify our selection effect or selection function was really kind of crucial. And this is from Julianne's paper from '97, I think from her thesis, where you can sort of see, this is the first image, and then we actually have, we can work on this data with algorithms and mask these bright stars, and then like bin and smooth and find the galaxy. So that I think was a big step forward. But still, some issues with background subtraction. The depth wasn't quite there. It was great for the time, right? But then about a decade ago, there was this very dramatic boost in our ability to detect these low surface brightness galaxies. And this was sort of commissioning of many different telescopes and surveys. So I'm showing here CFHT, the Hyper-SupremeCam survey, Dark Energy survey, and Dragonfly. And all of them really sort of, whenever we could have improved our surface brightness limit, we just found new things. So this is kind of a little bit of a history. Why low surface brightness imaging is hard. So it used to be that you sort of need more photon statistics, right? You're just not going deep enough. But there is another problem, which is that other than photon statistics, there is an issue with systematics. And this is how it looks like. So most, if not all of our telescopes are reflective telescopes. And as such, they are built from a lot of reflective surfaces. So what happens is that when you image some patch on the sky and you have a bright star or even a pretty bright galaxy, light is being scattered from the different optical components, and you get this sort of scattering disk or halo around the bright object. And this really sort of creates this noise floor that limits the surface brightness depth. So if I were to put my galaxy here, even if I see it, it will be hard to know if it's a real galaxy or just kind of an artifact or like a ghosting in my image. Here's another example from CFHT. And it's pretty old. Things are looking better right now because some components have been replaced, etc. But you see there are like all of these stars, and here is an elliptical galaxy. None of this light, kind of diffuse light, low surface brightness light around the object is actually not real galaxy light, it's actually scattered light. Okay, so there are many solutions, and I'll talk about some of them. So we built a telescope from lenses that we bought on Amazon or B&H. These are Canon telephoto lenses. They are commercial lenses designed and manufactured by Canon. And what Canon did is that they were designed for sort of sport photography and even paparazzi photography. So and I'll give an example. So what Canon did is that they developed this coating on the lens which prevents light from scattering or minimizes scattered light. So while paparazzi say that you want to take a picture of Biden drinking his morning coffee, and he's like exiting the White House with his coffee, and then there is a huge star, the sun, which is a Milky Way star, just like behind him, and then you have this like big ghost, and you just don't see Biden, right? So that's why they developed these telephoto lenses, and so we decided to try and see how it works with actual like professional astronomy. And each one of these is this like small refractor telescope, okay? But they are small, right? Like about that big, cost about 10K. And so we connected the CCD. This is the field of view, the one on yellow. This is the Rubin field of view, by the way, behind. So it's pretty big. And it worked great. Again, not enough sort of photons to actually do professional astronomy. But then we just added more of these lenses together. And then you collect all of the photons, so you point on the same point of the sky, same area of the sky, and just kind of collect the photons from all of them, right? So you're like effectively increasing the aperture of the telescope, right? Just adding more of these lenses. And then we added more, and then we added more. So this is the dragonfly telephoto array that we built between sort of 2014 and 2020, kind of between these two papers. And it's optimized for really, effectively it's a 1 meter telescope, which might not sound great, but it has such a superb optics that in terms of surface brightness imaging, kind of like the best at the time. You know, LSST, I think it's gonna do better, but it did great.
Can I?
Yes.
These are questions, but they sound like comments.
Yeah.
One is these lenses, being commercial cameras, they have way more optical elements. Commercial lenses,
Yeah.
I mean. They have way more optical elements than a normal telescope would have, because they can focus, because they're designed to focus without distortions at different focus. So is it really true that the coatings are so good that they overcome the fact that you have additional optical surfaces?
Yes, indeed.
Because
They do have a lot of components.
they have a lot of
70.
components. They have look
That's
inside.
right.
So many components. So
That's right.
well, I actually thought about this plan a long time ago, and I was like, no, because there's so many surfaces, it's got to be worse.
So yeah, so apparently it works.
That's incredible.
It works, and yeah, so the wings of the PSF are much reduced.
Yeah.
Less energy there.
So
by a lot.
that is incredible. So the second question / comment is that this is like a 1 meter telescope in terms of aperture.
Right.
It's not like a 1 meter telescope in terms of
The focal
angular
ratio.
resolution. Yeah.
Right, that's right.
Lambda
so
over D.
That's right. So the resolution is fairly small.
Yeah.
So the PSF is about.
But you officially don't care. But I'm
Right.
kind of
I mean,
interested in
I mean,
whether
I
you
kind
actually
of-
care.
I kind of care for some
Yeah.
science cases, but if you want to look at gigantic stellar streams or like the stellar halos of galaxies, if you want to look for like really tiny dwarf galaxies, yeah, you are limited, right? You won't go beyond. There is a sweet spot, definitely,
Yes, okay.
given the setup.
Good.
But
okay.
this isn't far from being atmosphere.
Right, because of the
That's right.
isoglatic
That's
patch
right.
is only slightly larger than its
That's right.
aperture. Yeah.
That's right.
No, it's pretty impressive. Anyway, it's good.
Yeah, it
But
works.
what are the
It's
pic-
cheap also,
It's
right?
cheap, yeah.
What are the pixel sizes in the end?
Around 2.5 arc seconds.
Okay.
Yeah.
Alright.
And like I have a lot more to say about the telescope, so I'm happy to talk about it later. But I have so much science to talk about that I really tried to like go quick.
And I respect that, but just give me one little
Yes.
sense of how important was building this to you? Were you're a builder of this, I believe.
Right.
So with the work that you did here, what fraction of it is building versus using?
So the building was quite easy, actually. You connect the lenses to, each lens has, its own filter, right? So GNR filters, it has a camera, it has a little computer, like Intel stick. Putting this whole thing, like the engineering is actually very, very simple.
Mm-hmm.
What was a lot harder was writing the reduction
I
pipeline.
bet.
Why? Because each exposure is actually 48 exposures, and then this one didn't behave, and in some of them we had satellite trails in some of the exposures. So what we did, and again I can talk about it for hours because that's what I did for like some of my thesis, was writing this kind of gate-based reduction. So each one of these images, say 10 minutes exposure, again 48 in one exposure, go through this like gate system, like was I focused enough, like the telescope, the lens specifically, and like many different tests. So now I think we're doing a lot better because a lot of students worked on it. But when I started, I had to kind of develop the whole thing. So I think that was the main component, understanding how to get like most out of the data.
Good.
Okay, because it's such great instrument that you don't want to lose it for like bad reduction.
That relates to things we talk about here. This is, in some sense, it's a software instrument.
Yes, absolutely.
Which is a very interesting.
computationally very, very.
Yeah, this is a
very-
computational telescope.
Yeah, absolutely, exactly. Which, we need to understand before LSST starts and,
Yes.
and Roman and, Euclid started already and others. All of our future in astronomy, really. Okay, so one of the fun things that we, kind of the first thing actually that we discovered is we looked at the coma cluster, that's a cluster of galaxies at 100 megaparsec, and we wanted to look at the intra-cluster light. So all of the very low surface brightness light kind of between all of these galaxies, but instead, we actually found a lot of these smudges. So these very low surface brightness galaxies, and this is how they look like in dragonfly, big pixels, okay? Let's look at one of them. So here is one of these galaxies, obviously, right? It's a galaxy, you can see right away. But if you take an image with Hubble, well, it's very faint, but it's there. It's kind of bright here. This is how it looks like. Can you see it? Sort of right here. So what was great and kind of surprising about this discovery is that these galaxies were very, very large intrinsically, or physically they were really large, sort of 3, 4, 5 kiloparsec, but they had stellar masses or luminosities of dwarf galaxies. So we call them ultra diffuse galaxies. Some people don't like this name, but whatever. And this is where they occupy this parameter space of size. Okay, have light radius as a function of surface brightness. So you have sort of Milky Way galaxies here. This is SDSS. You have dwarf galaxies here, and then you have kind of a new sort of almost class of galaxies right here. So big, low surface brightness. And someone asked me in our meeting yesterday, actually such galaxies, a few of them were known, and I think I was trying to kind of find the first paper in the literature that found these like gigantic low surface brightness galaxies, and it's this paper by Senjad and Danieli, and they say a new type of very large galaxy, 10 kiloparsec, low surface brightness, both early and late type, isolated. There are as yet no known examples in the local neighborhood. So a few of them were known. Here is the first one, by the way, photographic plates. It also has globular clusters, which we'll talk about in a second. And just to, again, kind of illustrate the difference between these big ultra diffuse galaxies, whatever, extended dwarf galaxies and normal dwarf galaxies, I'm comparing 2 Andromeda satellites, okay, kind of normal looking galaxies, and one of these ultra diffuse galaxies, and they're all placed at the same distance, okay? They all have the same stellar mass, but this one is really big, okay? Really big, like the way that we define galaxy sizes, right? Like half of the light is contained within this circle. So why did we think they were interesting? In terms of understanding dark matter, we thought that, hey, there aren't that many stars. Maybe we get this more sort of unobstructed view of the dark matter halo. And if you can trace the kinematics of the stars out to larger radii, you just probe more of the dark matter halo, right? You don't need to make so much assumption to what's going on in the outskirts, where in these galaxies, sort of probe the center, and then you need to, assume how sort of the outskirts look like. But, of course, it's really hard to get kinematics of these galaxies. So a few ways to do it. The first thing that we did is that we realized that a lot of these galaxies has these dots, and these are globular clusters. And so we went and got spectra of many of these globular clusters, and indeed, in many cases and in many galaxies, they were associated or gravitationally bound to the galaxy. So you can calculate the velocity dispersion and get some estimate of the dark matter. And this all happened kind of at the same time, where a lot of these integral field unit spectrographs came online. So this is the Keck KCWI, the Keck Cosmic Web Imager, which is a fantastic instrument where you basically get a spectrum from each one of these pixels. So you can integrate over all of the pixels and get a fairly high signal to noise. And so I want to sort of summarize a result that is really, really puzzling, that is compiling not only my work or my group work, but a lot of the literature work about how these galaxies look like in terms of how much dark matter they have compared to baryons. Okay, so let's look at the total matter. So the total matter over stars. So more dark matter is here as a function of total brightness. This is how it sort of looked before we started looking at a lot of these ultra diffuse galaxies at a brightness of roughly 10 to the 8. Okay, so many of the first follow-up studies found that these galaxies are very dark matter dominated, okay? Which for me made sense because something needs to kind of hold these galaxies together. And here is one of them, the one that we saw before, Dragonfly 44. This one is in the comet cluster. And then we also found these two galaxies, DF2 and DF4, that are very dark matter deficient, okay? So the way I like calling it is what you see is what you get. You don't need dark matter, right? You look at the motion of the stars, the velocity dispersion, it just fits perfectly to what you would expect only from the stars. So what you see is what you get. Okay, here is DF2, image with Hubble. Okay.
Are those in a cluster? Or are they just on their own?
This one is in a group. This one we thought is in a comet cluster. We did many follow-up studies. Now we think that it's falling into the comet cluster in a little group of like 3 or 4 galaxies. So yeah, so MOND is not going to work here, and it's not going to work here. Okay, don't want to talk about MOND.
What exactly is the y-axis? Because shouldn't it be greater
Oh, so
than
this is the dynamical mass to light ratio. So all of the matter over kind of the stars, or just, you know, the baryonic matter. And this
shouldn't it always be greater than 1, or is it defined in some strange way? Like all the matter is always more than just the stars.
Is that mass over light, or is it mass over mass?
It's mass over mass. But they're measurements. You're dividing two noisy measurements.
Why isn't it always above 1? That's what I'm wondering.
Why it's always above 1?
No, it should be above 1, I would think, no?
I mean, all the points
He's
of the
saying that
system
the
is
mass
wrong.
divided by the mass always needs to be greater than 1.
It's total mass divided
Oh,
by
so
some-
it's probably over light.
But there could be.
And I just simplified the, or
Well,
maybe
but-
I didn't.
But I think David's right, they're measurements, right? Like, you could measure 0.7,
Yeah,
whatever's.
Seems
You're
like-
dividing two
I mean,
noisy
I-
measurements.
okay.
That's
So I
right.
guess there's 2 different ways to measure. Like you measure total mass from, you're not adding the stars within the total mass. That's you're just counting the mass from the
Yes.
kinematics or something.
that's right. Yeah, that's right. Okay, so to me, like what's really interesting here, and you know, all this, that took like many years and many groups and many telescopes, so it's not that like, hey, this is how it looks like, it took time, and we were puzzled after each one of these points. But to me, what's really amazing is that, first of all, they are completely like, you know, all over the place, but they span 4 orders of magnitude in this dynamical mass to light ratio, which I think means that we, you know, by sort of revealing this kind of low surface brightness, you know, new parameter space, we just find a lot of different types of objects, and it's really kind of probably a mixed bag of galaxies, right, that were formed in many different ways.
But you know, if somebody was feeling very critical, they could say that the ones below the line are consistent with being on the line. They're only
This
off
one?
by, yeah, these two are only off
Yeah.
by 1.5 signals.
That's
so
fair.
They could be on
That's
the line.
fair. Yeah, that's fair.
It's definitely, I'm not undermining anything here, it's super interesting.
Yeah, there
But-
are actually new measurements. So for example, this one,
But
so this is
worth-
DF4, so it was done initially with global clusters, and there was a recent paper by a Yale graduate student that actually also did it with the IFU, with KCWI, and now, you know, their bars are much smaller. It's actually kind of more extreme than DF2 in a sense, but yeah.
To my knowledge, there's no galaxies known. Well, I guess you have a couple dots there, but there are basically very few galaxies that are conceivably stellar dominated.
I mean, these two,
Yeah, and then there's maybe a couple of the open squares that could be.
that's
I
right,
think
but
most
that's
of them
within the
are-
half-life radius.
Yeah, right.
Right?
Yeah, exactly.
These galaxies are actually lower mass, so within the half-life
Yeah.
radius, you know, is a bit more constraining on how
Yeah.
much dark matter you have.
Yeah.
Okay,
I'm sorry, I'm really
Yes.
confused. What is the
Oh, no.
the line?
ask me everything.
The line. What is that?
Oh, that's someone, I mean,
Is that?
these were like all kind of literature values.
Oh,
Okay,
so it's
the
that.
open-
Why do we expect it to have that behavior actually?
I mean, that's like star formation, you know, like dwarf galaxies are not very efficient at forming stars, so they are
Okay.
dark matter dominated. Same for galaxy clusters. Milky Way galaxies are kind of efficient at the center.
Okay.
Yeah.
It also
It's
has
like
a
the
stellar
efficiency
amount of that.
relationship reversed.
Yes. Yeah. If you flip it. Yeah. Okay.
Oh, it's a medal plot upside down. Okay. Yeah.
We'll ask her to put that up at the end again, and
Yes.
we'll talk about the
Yes.
telepathy.
Perfect. Okay. So, that sort of gave us a sense of like how much dark matter maybe these galaxies have, and indeed, people were trying to see, is this like consistent with Bond or with this model or that model, but then can we say something about the shape, okay? So the distribution, whether these galaxies have this like cuspy dark matter halo, where the dark matter is more concentrated towards the center, or NFW, as predicted by CDM maybe, if you don't include baryons, or the density profile kind of flattens, it is more kind of like a core shape, right? So I think you're probably sort of familiar with the cusp core problem. I don't think it's really a problem, but we wanna try and have actually a measurement of the shape. Now, this is really hard from the following reasons. So here's the same Dragonfly 44, and we got tons of data with Keck, and we measured the velocity dispersion profile, okay? Velocity dispersion is a function of the distance from the center of the galaxy. These are the points. And then we did this like genes analysis, and we saw that we can both fit an NFW and fit a core. This is not a new result. This is known as the mass anisotropy degeneracy, right? So you can sort of work it out with both models. You just need to change the total halo mass and the anisotropy, which is how much of the velocity component is radial versus tangential. So that's a problem. And let's look at one more example. So this is similar. This is the sort of a similar measurement of the Fornax dwarf galaxy. So it's a dwarf galaxy in the Milky Way. And here, I'm not loving this figure. It's a bit messy. But just the point here is that you can even try to fit different dark matter models, so SIDM and maybe warm dark matter, and they all sort of do okay. Like they're all consistent with really saying, there should be dark matter in this galaxy, but we cannot really say which one is better. So in other words, actually kinematics for understanding the distribution is actually a very inconclusive probe. And if we look again at Fornax, the Fornax dwarf galaxy, other than dark matter and stars, it also has some globular clusters, about 5, maybe 6. And these globular clusters, when they orbit this galaxy, they have quite different orbits than the stars. And this is because this effect called gravitational dynamical friction, which is when these fairly massive tracers move through the halo, they interact, they do all of these like microscopic interactions, right, with the particles that makes up the halo, both the dark matter and the stars. They exchange energy and they slowly decelerate and spiral in, right? And then if you kind of integrate over all of these little microscopic interactions, you can, in the continuum limit, you can calculate the dynamical, the dynamic friction time scale, so how much time it's going to take them to decelerate and sink all the way to the center. And this strongly depends on the velocity, but it also goes as 1 over the mass of my particle, and it also depends on the shape, on the density or the shape, kind of the local density of the halo. And so this is what Scott Romain did for his thesis at Princeton. So this is the so-called Fornax timing problem. So the reasoning was Fornax is an old galaxy. We can try to calculate how much time it should take for these clusters to sink all the way to the center. And what he concluded is that there should be a star cluster, a globular cluster at the center. It's massive enough, the galaxy is low mass enough, it had enough time, and maybe even form a nuclear star cluster. But there is no nuclear star cluster at Fornax, and so the conclusion was that Fornax likely has a cored dark matter halo, and then the clusters stall due to this effect called core stalling. So if the galaxy, if the dark matter halo had a cusp, they should quickly spiral in and make it all the way to the center, merge with each other and form a nuclear star cluster, or even just sink to the center. But if it has a core and the density profile kind of flattens, we have this effect called core stalling again, where they just stall sort of around the center. So Fornax has been kind of the main tool where galaxies people have been like kind of studying, kind of applying this idea, but it only has 5 globular clusters. And when we started looking with Dragonfly and other telescopes at galaxies beyond the Milky Way, we found really, really incredible galaxies that have a lot more globular clusters. So here is one of them. I know it doesn't look that interesting yet, but this is UTG1. We thought it looks really interesting, even just looking at it from the ground, because it had this sort of like overdensity of point sources and kind of this like very low surface brightness stellar body. And this is how it looks like when it was imaged with Hubble. And to me, when I first saw it, I just thought it looks like a cluster of clusters, because it has so little low surface brightness kind of stellar body, but a lot of these very massive and kind of dense globular clusters. Okay, so this galaxy is interesting for many reasons. One of them being the fact that it's a 10 to the 8 solar mass galaxy. Okay, so it's even less than it's really kind of a dwarf galaxy, a bright dwarf galaxy. From you missed my first slide, but it's a bright dwarf galaxy. But it has 54 globular clusters. And if you count how many stars you have in these clusters and you compare it to the kind of total mass of the galaxy, it's, I didn't write it here, it's 15%. So 15%, 1/5 of the stars are in globular clusters. In the Milky Way, about 0.5% of the stars are in globular clusters. It's not the same type of galaxy, so it's not really comparable, but it's really extreme in that sense. So it's interesting for thinking about extreme star formation and high redshift and all of that stuff. But in the context of dynamical friction, look at this thing again. So now I'm showing the same galaxy, but I masked, okay, I kind of masked from the image everything that is not related to the galaxy, so you can see this beauty. And then what you will see is the most massive clusters are at the center, right? Like we would expect from dynamical friction. I saw it, I was like, whoa, we're seeing dynamical friction by eye in this galaxy, because it also has so many clusters, right? So that was the first example that I saw, which you sort of have this really like clean view. So this is how, this is sort of measured, the projected distance from the center is a function of the star mass, and we do see this mass segregation. On average, the more massive ones are at the center compared to the less massive ones. And what we did, a student that I worked with at the Weizmann Institute that left astronomy, unfortunately, he was excellent. What he did is that he set up a simulation with a static dark matter halo, and he put these point particles, which are the globular clusters, and we try sort of a variety of dark matter halos to see whether we can, one, reproduce this mass segregation if we start with the distribution of globular clusters that are not mass segregated, and can we say something about how much dark matter this galaxy has and about the shape. So I'm not giving you any of the simulation details because I kind of want to show you a few more stuff. But what we found, and again, we don't have any kinematic measurements here, right? This is just looking at this image and kind of, knowing the masses of these globular clusters and running a simulation and trying to match what we see in the simulation to what we see in the image. No spectroscopy here. And what we found is that this galaxy has to have a lot of dark matter, so it needs to be dark matter dominated in order for these clusters to sort of sink all the way to the center in a sort of a reasonable time and kind of a reasonable initial conditions, but it likely also has a core. And again, this is only from the image, right, from photometry. So I think this is really cool because this is sort of evidence for dark matter, which is not coming from kinematics. Yes?
Is it?
Oh, go ahead.
How can we rule out that the clusters don't happen to form, more massive clusters at the center, just formation?
Yeah.
Like you have a hotter gas, whatever, at the center.
Yeah, we cannot because we don't know like how globular clusters form. So we cannot. But in the next example that I show you, I think we found like another example that sort of proves this same point in a different way. But yeah, we don't know. I mean, this is definitely like kind of the caveats in our in this study.
So what do you assume in the simulation for the starting point? Like they're everywhere uniformly?
Yeah, so they are not mass segregated. That's what we started. We actually did some runs where they have some mass segregation, and we got something sort of similar. There are some very high resolution simulations that sort of go only all the way to redshift of 2, really from the last sort of year. And it seems like actually at the center, not many of them form because they are being disrupted by GMCs. And so actually, if anything, I think they'll form more sort of in the outskirts. But yeah, I mean, we don't know.
So the typical 10 to the 8 solar mass galaxy in stars, you know, only has like one globular cluster or something. And is the story then that probably they started with 50 or 100 even in those cases and they're all destroyed?
So
Is that
the story I speculated
Yeah.
in the paper, not in this paper, but in the observational paper, is that this galaxy, almost all of it was formed in clusters. And then sort of the stars that we see, this is due to, you know, the low mass ones that got disrupted, right, from the Schechter function, and two-body relaxation. So stars that slowly,
So it starts with not with a big Gaussian peak of clusters, starts with a Schechter function.
yes, you
And
lose
then
all of the
yeah.
low mass clusters.
Okay.
And then, yeah, the mass function of the clusters is really normal, kind of the peak is at the right place, the width is kind of the canonical one, yeah, universal
Okay,
one.
and but if you but somehow in an SMC that, you know, like what's different about this than being in the typical, is it just being in a more massive halo? Like what causes this to happen in this situation
I
but
don't know. I don't know.
not in your typical 10 to the 8 solar mass
I don't know.
galaxy?
I don't know how this galaxy was formed. That's a good question.
But I don't mean why it's so low surface brightness. I mean what
Right.
happened to the globulars.
I mean, I think this.
Like what happened to the globulars of the other 10 to the 8 solar mass galaxies that don't have any? Like why you're saying in these galaxies they don't get destroyed.
Right. No, they do. They do get destroyed. You just
Oh,
have
sorry, but lots of them don't.
the same. But I mean, so the mass function of the global cluster, global like the GCLF,
Yeah.
is similar, very similar in shape, and in shape to the SMC one.
Okay. How many does the SMC have? I thought it had like of order 1.
No,
No?
I think a lot more.
A lot more.
Yeah.
Okay, so I'm just remembering that.
I think a lot more.
Okay.
And I think it's
I
also
didn't know it had,
it's
like,
more
50.
massive than this one, than this galaxy, right?
Yeah.
It's a bit more than
A bit more
10 to the
mass. It's a few times
eight. A
more
few times
massive
10
than
to the eight.
stars.
Yeah. I mean, what's unique about this galaxy is mostly sort of the ratio or how many stars you have in the clusters compared to the entire galaxy.
Right. Yeah,
Um,
that's very different.
yeah. Okay, how much? I don't have a.
Sorry.
Uh,
There's
I
a
don't-
clock up there that's an hour slow. That one.
Okay. Let me skip one little thing and move to this part because I think that will be fun. So, and I'll go through it quickly. I did start 5 minutes late, so I have 5 more minutes at least. Okay, so the other thing that I want to talk about is satellite galaxies around Milky Way-like galaxies. So these dwarf galaxies, I don't need to give this introduction again, but they live in these little dark matter halos that orbit in this big central potential well, right? Like this is the Milky Way here in the center. We have all of these dark matter subhalos, and we can try to trace them with these dwarf galaxies. So, as I said at the beginning, we want to kind of put the Milky Way in context. So I'm going to talk about what has been done in terms of trying to map these satellite dwarf galaxies beyond the Milky Way. So this is satellite sensitivity as a function on how many of these galaxy groups or hosts, like Milky Way hosts, we know about. And this is the direction we want to go, right? Better statistics and also more sensitive, but also harder. So going down the luminosity function of these galaxies. So in the Milky Way, we have one galaxy, and we can go now even lower, maybe not in a complete way, but we can really get to these like ultra-faint dwarfs. And then with something like SDSS, which is a spectroscopic survey, we can have many of them, but sort of one, but we're only sort of sensitive to LMC type of satellites. And then there was this work over the years of kind of trying to do things in the local volume, where we have, a few of these hosts, and we go sort of maybe almost reaching the ultra-faint dwarfs, but not quite. And then the SAGA survey recently completed mapping the satellite galaxies around 100 Milky Way-like galaxies, going down all the way to roughly a few times 10 to the 7, again, in terms of the sensitivity, right, the stellar mass of the satellites. And I'm gonna show you a little bit of work with the ELVES survey, where we kind of tried to push the number of hosts, but really kind of getting almost to the ultra-faint regime. So this is the survey. It's called the Exploration of Local Volume Satellites. And this is a volume complete sample. So all of the massive galaxies above 10 to the 10 solar masses in the local volume. So that's a volume extends out to 10 megaparsec. So everything there we took. When I say we, I mean Scott Carlson, a graduate student that graduated from Princeton. And what Scott did is that he went and looked at the sort of the projected kind of halos around all of these massive galaxies, massive, Milky Way-like galaxies. Again, a volume complete sample, and found all of these little low surface brightness candidates. But then, and this is a challenge I'm not going to talk about because I don't have time, he measured distances to all of these galaxies, either by the tip of the red giant branch technique, if there were Hubble data, or by using the surface brightness fluctuations technique, where you can measure distances at lower accuracy, but using ground-based data. And I don't have time to describe it, but I think it's going to be a very crucial methodology that we're going to use in all of our future surveys. So this is the cumulative mass function of the satellite galaxies from all of these groups. So the first thing that we see is that there is really big variation. And there is this pretty significant host-to-host scatter. And just to give you a sense, we mapped around 320 satellites around 30 hosts. So roughly, on average, 10 per host. If we look at the satellite richness, so how many satellites as a function of the absolute magnitude, we see that on average, more massive groups are orbited by more massive galaxies. We also see that the Milky Way and M31 seem pretty typical. Okay, so that was one of the goals. And then we can also compare it to predictions from simulation, assuming cold dark matter. And so what we see here again, this is the richness of the number of satellites as a function of the stellar mass of the host. And the blue shades here sort of show the results from a simulation. And we see that this pretty big scatter is consistent with the predictions from the simulation. The other thing that we can try to do is to put some constraints on the faint end of the stellar to halo mass relation. This is really hard. I'm not entirely sure that what we did is legit yet. I'm still trying to convince myself. But what we can do is that we can sort of repeat what people have been doing with abundance matching, right? You take your sample of dwarf galaxies, you take a simulation, try to match them and sort of constrain the slope and the scatter. This is extremely hard, right, Jeremy? But we had this nice sample, 300 satellites sort of stacked together. So to skip the details, that's what we did. And this is what we found. So this is the result, the red line here. And what we found is that it's extremely consistent if you do the same exercise only using the Milky Way satellites. Okay, so if you only use this one galaxy and you look at the satellites of the Milky Way, so that's the result from Nadler. Okay, so this one here, you get really, really consistent results. It's also consistent with the new universe machine result from Beruzzi, which is great.
So just so I understand this, this is like the stellar to subhalo mass relation.
Correct,
from
yeah.
the satellites.
Yes,
Okay,
yeah,
great.
Yeah. So the slope and the scatter are consistent with the same ones, the same values that were inferred just from the Milky Way. And we're not sure if it means that the satellite stellar to halo mass relation is maybe universal. And so if I have some galaxy group, I can sort of predict how many satellites I should have if I know how many dark matter subhalo it has. I think I'm running out of time, so I'll just show one more thing, which is that we're now working on repeating ELVES, so the same survey, but sort of extending to lower mass hosts. Okay, so looking at dwarf galaxies, kind of LMC, SMC mass, but isolated, okay, and looking at the satellites of the dwarf galaxies. So these are two predictions. So this is one prediction using this stellar to halo-mass relation that we got from the ELVES dwarfs, and this is the Baruzzi 2013 prediction, and these are our very preliminary results, all done by Joshua and Lee, a graduate student at Princeton. So this is what we have currently, and he eventually is going to have sort of a 40 of these hosts. But so far it seems like the stellar to halo-mass relation we constrained from the more massive hosts, right, from ELVES, sort of works really well, or predicts really well the satellite population for lower mass hosts, dwarf mass hosts.
What are you using for this again? Maybe you said
So this is using many different
whatever you
datasets,
can get your hands on.
HSC, legacy surveys, but then you find the candidates, but then you need to go to something like Magellan IMAX and do imaging to get deeper data to do the surface brightness fluctuations to measure the distance.
I see.
So it's a lot of work, but it's working really well. This is kind of hard because you also just don't expect to have so many satellites, right, down to our detection limit. So yeah, so this is kind of hard observationally. And I think I'm gonna skip the very last part and just go to my summary slide. And if you have more questions, I'm happy to answer. But thanks for listening. It was a lot, you know.
For the low surface brightness population, is there some understanding of how if we're sort of trying to account for all the stars, how much do we have to worry about them? Like, do they contain a lot of stars? Like, do you have an estimate
All the
of
stars in the universe?
yeah, just like when we look at whatever mass halos you found them in, are they a substantial portion of the stars in those halos could be in these low surface brightness things, or are they?
So you mean for a fixed halo mass?
Yeah, I mean, I'm more asking I think I'm asking, in at least bright things, or rather massive things, because
Massive
obviously
halos.
everything at low mass is in very low surface brightness things, but things that are, because these things have similar mass halo, not so far from the Milky Way, right?
The stellar mass?
No,
Or the halo mass?
the halo mass.
I mean, some, right?
Yeah.
So some have, none really have, only a few have like really, really massive halos.
Right, not 10 to the 12, but
Not quite.
Yeah.
Again, it's hard because, you need to do kind of like wolf estimator and then assume something on the other half, right?
but those estimates you had were high 10 to the 10,
Right.
low 10 to the 11.
Right.
So I mean, for like halos like that, are there potentially many more stars we've just never observed?
I don't think so.
Okay.
I don't think so. I think the stars for like a fixed sort of 10 to the 10 halo mass, the total amount of stars is still going to be dominated by the bright galaxies.
They're not,
Bright
you don't think there are
galaxies.
enough of these low surface brightness things?
No, I don't think
Okay.
so. Having said that, we haven't sort of mapped everything. We've mostly been looking at clusters and groups just because it's easier in a sense, but we are looking at sort of the field at the moment. It's a lot harder because you find all of these candidates and you need to get these like follow-up data and measure distances, but we are doing it. Like we have this wide field service with Dragonfly, and that was what Marla was talking about. But no, I don't think they are like dominating.
Okay.
I mean, I can tell you that in groups, like around Milky Way groups, and there are two results from two different groups. Like on average, there is between like sort of half to one of these like very extended low surface brightness galaxies
Per group,
per group,
yeah.
down to some detection limit.
And we certainly don't have one?
In the Milky Way?
Yeah.
So I mean, some people
Like, would
say
we
like
see it?
Antlia 2 maybe, right? Because it's like really low surface brightness, but like Antlia 2 is like
Yeah.
being disrupted many of these galaxies are actually, they look dynamically stable. So I think there are different creatures. So personally, I don't think there is a similar galaxy in the Milky Way. Some people predict there should be about 5 within 2.5 megaparsec.
Oh. Is anything known about the abundances of the stars in these ultra low surface brightness?
Yeah, the UDGs,
Yeah.
the ultra diffuse.
Is it possible to know?
Is it what?
Is it possible to know with the
Yeah,
red
there
giant
are.
branch or something?
Yes, there are a few studies of abundances. I mean, not, there are also, again, the same way there are like a mixed bag in terms of their like kinematics, that goes the same for, there are some that are star forming and some that are completely quenched. And so I don't have a complete answer to give you, but I can get back to you, but I'm not sure. Yes.
For the Dragonfly telescope you built, you said you chose the Canon cameras because they scatter less light.
Yeah, the lenses, right, yeah,
Yeah.
the lenses themselves.
Is it at all possible that the next lens we build for an observatory could have that in it, or is that like
Magical coating, put it on everything, right?
So,
it's?
I don't think it's
the
gonna
image
be
sort of
efficient. So, most of our telescopes these days are built out of mirrors.
right.
And they just have, a primary mirror and a secondary mirror and another mirror. So there are not lenses that we don't build, we build some refractory telescopes, I guess, but they're usually pretty small. I'm not an expert on the coding technology. It's actually also kind of confidential by Canon, we
Yeah.
don't really know what's going on. We kind of know what's going on, but not sure it's gonna be the most efficient thing to do. I'm not sure we need it, actually.
Gotcha.
I didn't say that we're building, at the late stages actually, of building a bigger Dragonfly, which has 168 lenses, and they have narrowband filters. It's an amazing project. It's led by Deb Lockhurst, who is a research scientist at University of Victoria, and she designed this filter tilter. So you put the filter in front of the lens, and it sits on this thing that she sort of 3D printed, and you can tilt the filter and change the essential wavelength. Isn't that amazing? So you can sort of scan, right? Redshift potentially, but really kind of scan velocities. So that's gonna come up sort of soon in the next year or two. But yeah, I guess you can just, it's gonna be cheaper and easier to just add more lenses, but then it's a computational telescope because it's really hard to deal with. So we pay AWS a lot of money. Yes.
The globular clusters, the photo image you showed us with all the bigger ones in the center.
Yeah.
So is the picture you have in mind that if I had some infinite resolution, I should be able to see a bunch of tidal streams everywhere?
Mhm.
Like a
Oh
bunch
my
of
God.
noodles?
Yeah, probably for some of them. Yeah, I think
And what
we
would
can
it
see
take to actually see?
at 25 megaparsec.
I don't know.
Not anytime soon, but maybe we can find more nearby galaxies and look at that. But yeah,
I think that might fully resolve this cusp core thing if you saw the tails. Because there would be if you could see a few of the tails, I think there would be a lot of information.
yeah,
Or is there a way to detect them? Because it sounds like there are many more globular clusters there than in more standard galaxies. So it's more
yeah, absolutely.
They're being more active.
This is the most
Yeah.
globular cluster rich dwarf galaxy.
So is
in
there any way
existence.
to detect these streams in a statistical way, like some kind of graininess?
In this
rather
one
than-
galaxy,
You know what I mean? Like,
I mean,
like you don't see them
maybe,
individually, but like some.
so this one sits at 26 megaparsec, which is, the globular clusters themselves are kind of also just maybe resolved with the camera that we use on Hubble, which might not be available anymore soon, actually, because they are decommissioning some of the cameras, unfortunately. But if we find a similar, there is no reason to think we shouldn't find another one, like closer by, maybe it's extremely unique, then we found it, right? Then yeah, but I think this is a really promising direction. I was really excited about this work. It has a lot of simplifications in the simulation, right? Even core stalling is kind of, put into the simulation in a semi-analytical way, calibrated from n-body simulation. So we have a student now that runs a very high resolution N-body simulation where even the halo is an N-body. So there are so many improvements we can still make, but I just thought it's really cool because you sort of detect the need for dark matter without kinematics, right? Just from the dynamic law sort of considerations of this system. I didn't show, can I show like a little slide?
Yes.
So we sort of did a similar work with Shany who is currently a graduate student at Princeton, where we flipped the problem and we looked for a galaxy that has a lot of globular clusters, but also a nuclear star cluster. Okay, so this is flipping the Fornax timing problem and asking, if this galaxy has a nuclear star cluster, does it have to have a cusp, right? Otherwise, the clusters will stall, will never form the nuclear star cluster. So Shany did the same kind of simulations, like he rewrote the same simulations, improved some things, but then, let me just show you that. I think this is really, really cool. So the way we compare the result of the simulation and the observations is in the following way. So this is the globular cluster mass function, okay? And then the observed one is this purple histogram here. So you can see we have the nuclear star cluster. Then we have this deficiency here, right? Compared to kind of like the log normal distribution that we would expect. If we run the simulation with a chord halo, we never form this nuclear star cluster and this deficiency here at the high mass N. But if we run it with the cuspy halo, which is this result here, we can form the nuclear star cluster and this deficiency here of massive clusters. So these massive clusters actually sink all the way to the center and form the nuclear star cluster only in the case of a cuspy halo. So this is kind of a different example. What I think we need to do now is to kind of run it for many galaxies and see, whether some are cuspy and some are chord, and how do they look like, and do they have, does it correlate with other properties? And so that's also one, I think, interesting direction.
But this is still, I mean, this is a good thing to be doing, but this is still in some sense a toy, in the sense that these are not, like in a cosmological context, the dark matter halo could be pretty complicated, right? It would have multiple substructures and
Indeed.
so it's actually, unfortunately, it's hard to ask, you're asking kind of counterfactual questions between chord and cuspy, but then within the context of like some CDM simulation, you don't get to choose, you just get what you get.
Right.
So I think toy simulations is a good way to go, but it would be very interesting to me whether substructure changes this question at all.
Agreed. I think,
Because it gets back to your original question of like, could you learn things about the dark sector from these pristine galaxies?
Is this a case where you can measure the dynamics in the center and say something about the mass profile? Or is the
Modulo beta.
Yeah, that's the
Modulo
issue.
beta.
Yeah, that's the issue.
The velocity anisotropy.
Yeah,
sure, but
Still.
yeah.
but you do have
I guess
But
you
in
can
the
do
other-
kind of like the enclosed, kind of like, that's the problem, I mean, that's why we're trying to find like a different way to say
So
something about the shape.
So it's not just it's
I'm not saying we solved it, by the
so
way.
even having higher significance, because in the dwarf galaxies, like you don't have a lot of information in the center. That's one of the problems, right? Because you only have so many stars.
For the ones that are not like really
Yeah,
nearby.
Yeah, but this does have this has a cluster of stars at the center.
Yeah, exactly.
So
I mean, actually, like in this case, more than having the cluster in the center, I mean, clusters can form at the center maybe and accrete more stars and form a nuclear star cluster. We know that sometimes they form like that, right, from the star populations. But in this case, what I thought was cool is this, we see that like we lost the high mass ones, right? And that's only because there are so many clusters, star clusters in this galaxy that we populate, like we sample the entire mass function. That's why, 4NX is not enough, you have 5, right? But
So
here you
there's
sort of like have them all.
if you count the core cluster, the central cluster in the list of clusters, then you have like a cluster mass gap.
Exactly. And I want to say one more thing, in case people have ideas, which is that what we also find in these toy simulations is that it only takes about 5 gigayears for the nuclear star cluster to form, kind of on average. Okay, so to sink to the center, form the nuclear star cluster, and then it just sits there for 5 gigayears. So I think that it might form a core by just sitting there, because it's like comparable in kind of enclosed mass to how much dark matter you have at the center.
It probably
So-
depends on whether there's a black hole.
I was gonna ask.
Yes. Right, that's right. But
Are there X-ray sources? Have you looked for like radio and X-ray sources?
not for these galaxies, but like, I think some people look for.
Well, people look for dark matter annihilation. These are also
Yeah.
interesting sources for dark matter annihilation.
Yeah, that's a good point. And also just repeating this exercise with whatever SIDM dynamic of friction and see what do we get, is interesting, right? It's just a different way of sort of probing maybe the shape of the dark matter halo. But yeah, I'm working with a student now that puts a very massive nuclear star cluster at the center of the halo, which is made out of individual star particles, and we're gonna see what's gonna happen. But again, I mean, these are very simple simulations. I'm also an observer, so but I think it's really, really fun. Yeah.
Let's thank Shany.
Thank you.
Would you mind putting up that M star
Yes.
plot again?
No.
The-
This one?
Thanks for
This
that.
one. Yeah. So we were just looking at Journal Club yesterday at a recent paper about 12 NGC 1237, which something where there's a rotation curve, not a lot of dark matter is needed to explain the rotation curve. And I was making the claim to the students yesterday that there are actually quite a few galaxies with rotation curves, which in the stellar area within 5 or 10 kiloparsecs are pretty darn consistent with no dark matter.
I mean, it's just dominated by stars, right?
It's just dominated by stars,
It doesn't mean
right?
that the galaxy has no dark matter.
And there's
Yeah.
face-on, edge-on issues, right?
That's for,
Like there's
that's right.
inclination issues.
Well, there's inclination issues. I don't think there are any issues.
Oh, you're talking
though.
about the
I
ones
think
about
it's
the
just.
Tully-Fisher relation?
I just think there's
Yeah.
not a lot of dark matter in the centers of those galaxies. I
Maybe.
think the observations are right, but I think those live on the lower edge of this distribution.
Probably,
Yeah.
I don't know
But
what this sample
I
is,
think-
but
Looks
I
like
think
because
it's
there's some by one, right? There's some here near one.
Yeah,
So that
and
would
this
suggest yes.
it says mass to light ratio. So no dark matter. I'm not sure is at 1 in this plot.
Maybe not.
So I think what's more constraining
Yeah.
in these galaxies is that if you usually have a dark matter halo, okay, this dark matter halo, and then you have the galaxy, okay,
Yeah.
the stars, you sort of probe that, right?
Yeah,
And so you are
yeah,
Yeah.
star
exactly.
dominated,
Yep.
right? In the case of this extended galaxy, remember that I showed like the image, right, compared to the Andromeda ones. Again, you have the dark matter halo. I don't know, maybe dark is getting, I'm not sure. And then you have the stars. And then maybe you have enough globular clusters or something where you can use an IQ or whatever, and you can again look out to the half-life radius. And then within that, again, for the other galaxies, you're just more constraining, right?
Yeah.
But that depends on if the dark matter profile is about the same, I guess.
You mean it might be more extended?
I don't know anything
I
about
don't know
this, but
but that would make even more
I
dark.
don't know
That would
either.
make them go even further up, right? Yeah.
Yes,
I mean,
correct.
most of the things on the right probably are. I don't know what that total mass is, but there's a lot hidden. I guess it's within R1 half.
Yes, yeah.
Okay. So that is still where the stars are.
Yeah.
Yeah. Yeah. Anyway, I just wanted to.
But I think the ones above the Tully-Fisher relation, I think the issue is the inclination. That's kind of like the unsettled problem.
The
I
ones
think,
above the Tully-Fisher
Yeah.
relation. Does that mean they have higher velocities?
lower velocities,
Lower
more
velocities.
bar, yeah.
Yeah, I'm just wondering which way we've
Which way
oriented
you
Yeah,
Tully-Fisher.
yeah. So dark matter deficient.
Oh, right.
Or yeah,
Discs.
the discs. And over there, I think.
Yeah. Yeah, because it's that direction you can. Yeah, that direction you need the inclination can be a problem.
Yeah, that's why we just need to look at these like dispersion supported systems, and then it's hard, right? But you get something maybe a bit.
Right,
less
but the big advantage of the rotation supported systems is the kinematics are much more
than-
instructive about what the dark matter is.
Yeah.
So that's the trade-off. But yeah. I just want to say, I really admire what you guys did with Dragonfly. I really think that's a really impressive piece of work. And I know how hard that is. Like, that's why I asked you to just say a word about it, because
Yeah,
I want
no,
it,
it took
because
a lot of time.
we've thought a lot about instrumentation systems that are very distributed, you know, like where you would build, because from a pure mechanical like cost, it would be far cheaper to build 100 1 meters than 1 10 meter.
And even like
You
with
know,
spectrographs, right?
With spectrographs
Yeah,
even, yes, so
I
we've
know.
thought about it would be cheaper,
Yeah.
but the software complexity is so high
Yeah.
that whenever we like think about whether we could go in that direction, we always decide we can't,
Yeah,
because we would need a fucking army of software people,
which we didn't have.
which you didn't have. Exactly, and so for me,
Yeah.
like Dragonfly is obviously the right thing to do, but one of the reasons it's so intimidating is that you have to build
Yeah,
this software system where you cannot assume that all your systems are equivalent.
exactly.
Like if they were all actually equivalent, like it was dipoles in the Australian desert,
Right.
then it's just a correlation problem.
Yeah.
But here it's
I think the radio astronomers would
would be
also
pissed.
argue.
They would be pissed
What
to
are you
hear me
talking
say
about?
that. But so
this giant
So I think-
calibration matrix.
well, right, and in fact, the complexity of a software project goes up with the number of pieces of hardware,
Yeah,
as well as the overall scale of your project. So this project is not huge scale, but the number of pieces of hardware is very large.
and like I won't lie, there were like a lot of issues like along the way. I think one thing that helped is that we sort of kind of slowly, I mean, at the end we developed it pretty quickly. I mean, in just one thesis project for me.
Yeah.
But I think it helped that we sort of started with just like one lens and got data and kind
Yes.
of built slowly like the different
Yeah.
sort of algorithms for each one of the steps in
That's
this
right,
like gate system,
Iterative.
then we added more. Now it's like an amazing, now actually they finally hired the postdoc that actually deals with all the data and any improvements for like satellite trails, masking, that becomes like a big problem, for
Because one of the things we've been thinking a lot about is like training and funding for instrumentation, and especially the software side of instrumentation. So one of the reasons I love Dragonfly is that my kind of the thing I'm trying to push in astronomy is that we should think of new projects as software first. But there's a lot of expensive design decisions that go into instruments. Like
Yeah.
Dragonfly is the exact opposite of Express,
Yeah,
right?
right,
Express is an instrument that was built at Yale that is
right.
100% hardware and trying to make the software as simple as possible. And you guys were like 100% software and trying to make the hardware as
And
simple
you
as
get
possible.
more science out of it, like 100%.
Right, and I think the future is thinking of what's possible from a software perspective, in part because it makes your hardware much cheaper, in part because there's so much software development we can benefit from, like all this parallel
Right.
computing type
Yeah.
stuff, and then partly because you can constantly upgrade your system. Like upgrading Express
Yeah,
is like 3 years of like
no, here it's easy.
like lab work.
It's
Here
like
you
a
can have-
1 month project.
Yeah, you
right?
can literally have somebody build a punk pipeline,
Yeah,
and when it starts to work, you can.
but that's how it's done.
Yeah, exactly.
Like upgrading from like the,
Yeah.
10 to like
Yeah.
48 wasn't
Yeah.
hard.
Exactly.
I mean, what
So
are
it's
we
a
gonna
very
do with like
exciting
LSST?
project.
Like, do you feel like, I don't know, do you feel like LSST doing like enough effort thinking about the software? I feel
Well,
like
they're spending enough money.
enough money.
But they might not be thinking
I mean,
enough.
I'm personally like,
I mean,
They're not paying for
think,
the
I think
thinking.
the LSST data team is
No,
rather
they're
good.
Yeah.
No, they're good.
I think
Yeah.
they are rather
They're
good.
definitely good.
They have a lot of
I-
professional software engineers in
Yeah.
like.
no, I mean, I know, and I know all
It's
of them because some of them sit
Yeah.
in Princeton.
But that's
so-
why, for me, SKA is more like the future, because SKA is like obviously a software system with some hardware in it.
Yeah,
Whereas LSST is still a hardware project with very good software.
yeah,
And I think the future is gonna be software systems somehow.
yeah.
How big? You're talking for these Canon things, right? Like patents expire 20 years. You started this how long ago?
Yeah,
like,
yeah.
like whatever they're doing actually probably.
I bet it's not patented, I bet it's just a secret.
Yeah,
Oh, these
Nikon
trade
is
secrets.
making,
Oh.
yeah, Nikon is
Oh, you're
making
probably
like
right.
similar.
So what you
things
need is to
now.
get one of your grad students to get a job at Canon.
I'm not
That's
gonna
the
build
way
another
to
dragonfly, and I'm working on like 10 different other projects, so I think I'll put my student on some other.
Yeah, maybe.
Yeah.
Are there
I mean,
reflective?
Yeah,
Are there reflective designs that are better optically? Like, are there off-axis reflective designs or something that are better in terms of systematics? Because mirrors are better than
Commercial
glass.
uses, you mean?
Say again?
For commercial uses?
No, I mean for, like, could you, if you had arbitrary opportunity to design
Like the
a
coding
reflecting
technology.
telescope.
Oh, reflective test, oh.
Yeah, no, get rid of refraction, go to reflection,
Yeah.
but like try to minimize, like if you
Well, there's
really
the
had
Burl
made a
Schmidt.
telescope.
Yeah.
Burl Schmidt's not bad,
Yeah, it's
Mhm.
not
and it's
bad.
in a big tube.
Yes, right.
It's
So
really
you-
not bad.
What?
Yeah, it's
Yeah.
great. Like Chris Mijos has been doing this incredible low surface brightness work.
Yes, good,
with-
great,
with
yeah.
Yeah.
Yes, because a lot of it's because of the support structure.
Yeah.
Which is
Exactly.
That's so
the
embarrassing.
thing that holds the secondary mirror,
Yeah, it's so
right?
embarrassing that the
That's true
support
though.
structure.
It's just being reflected by the thing, right?
Yeah,
that
yeah.
holds like the other mirror. No, it's true though.
It's
Is it,
gross.
is it the stability of it or what? Why
I
the
mean, you
support
have
structure?
your
It's literally
primary
just the
mirror,
support
which-
structure just
Yeah.
makes your aperture complicated in that means
Yeah.
you have
Well,
Ref-
it'll
refraction
cause
and-
diffraction,
refraction and
yeah,
absorption.
but in also often you're actually, I mean, you have light baffles, but you want to actually, you actually don't want to usually restrict the airflow,
Yeah.
right? So usually you have light baffles, but you don't completely enclose the area of the telescope's in, because that's going to cause lots of turbulence, which will ruin the seeing. These guys don't care about seeing.
that helps. It helps.
And so in the Burl Schmidt, it's like a big tube,
Yeah.
and so it's just like completely baffled.
And I
And
think-
so it has very low.
But
scatter
support
light.
structure hurts you for a lot of reasons because it makes your aperture worse. But it also means there's all sorts of fucked up light paths where a photon can glance off of something and go in the wrong way, and you can't baffle it all. It's like it's
you
like
can't baffle light that's
impossible to
coming
baffle
through
it
the
all.
aperture,
Yeah.
through
Yeah.
the pupil.
And so it's all about support structure. So what we should really be working on is just levitation technology. So that the optical elements just levitate out in space and do this.
We just have it a big array of the right sort of magnets.
Yeah.
Exactly. Yeah, no. it's-
Set up your field and
And
There's
then-
really
and then-
deep reasons that
And the
that
entire
doesn't work.
telescope has to move in coordination,
Yes,
right?
exactly.
And
Yeah.
like points,
Or
like
just
pointing
this
is
could
perfect.
be on a helicopter. This could be a drone.
Guiding is super easy.
No,
Yeah.
seriously, it
Sounds
is-
like a 2050 project.
Yeah.
Oh, you're
Well,
thinking,
it's-
yeah,
it's-
you're thinking of
it's
this holding the
also-
secondary with the drone?
Yeah,
It's
every,
behind the
Oh my
secondary.
no,
God.
it's a cluster of drones. Every optical element is a cluster
An
of
array
drones.
of drones.
That sounds like something.
The drone
you can-
array.
Whose tolerances would be rough.
Yeah, but dragonfly is simple, and that's the secret behind it.
No,
right?
but the funny thing is, it's not simple if you take a saw and cut through one of those lenses. It's
Right.
insanely complicated.
Yeah.
That's the thing that surprised me when I first
Yeah.
heard about Dragonfly. I was
Yeah.
like, you can't win because you have too many optical surfaces.
Yeah.
But in the end, you're
That's
right.
right. Yeah.
You do win.
Yeah.
No, and Canon, like, there's a lot of money in reducing lens flare.
I mean,
Like, a lot of
now
money.
that you know about it, like you'll see it in like sport games and like wildlife photography.
No, when
Yeah,
you take
people-
just a normal camera and try to shoot lots of things, you get flare all over the place, and then they take these insane shots of NFL games.
Yeah, beautiful.
Yeah,
But you have
and
this,
it's
like,
not, it's hard to think about, we don't think of that as like, but that's a huge, it's a huge economic pressure on optics
Yeah.
that we can't possibly have.
But not meter scale optics, unfortunately.
No, unfortunately, not meter scale, right, not
Anyway,
meter
that
scale.
was terrific.
Yeah.
I have to go, so.
Yeah.
But thank you.
That connects to so many
Exactly,
interests
finally made
here,
it
it's
here.
really,
Yeah.
really good,
Yeah.
really good.
Yeah. They are.
You were a Peter student, Peter Van Doffen
Yeah.
student?
Yeah.
I have to say, I didn't think that project would work and it crushed.
Yeah. There are so much.
So
other
many
data.
interesting things came out, and so many interesting things came out, even though, as you are about to say, there's so many things that haven't even been done
I
yet.
need like 5 graduate students
Exactly,
to
yeah.
look at stuff at the wide field survey, which is the
Yeah.
final thing I submit
Yeah.
for my thesis.
Yeah.
But yeah, I am finding this really tiny low surface brightness dwarfs that I think are isolated in the field, kind of getting into the ultra-faint regime, and these are super interesting.
Yeah, isolated ones
They're
are more
like
interesting
very
for many
pristine, right?
reasons, yeah.
Like
Hey, I'm gonna be around.
okay, perfect.
Yeah.
Yeah, okay.
And I have to go meet with some deans, so I've gotta go here.
Oh,
That's
oh,
fine.
when was that? Oh,
No, no.
we have to go.
I gotta go, so I'm giving you to whoever's next, cause I gotta go. But that was